finally I'm ready. Sorry about the delay. So, my understanding is we've got a bunch of lab questions about the electrical properties lab. Maybe not a bunch, but at least a few?
Yeah,
At least a few. Okay. Okay, what questions do we have?
I had one question about how voltage drop across the semiconductor changes with temperature.
Yes, okay. So most of the phenomena we're looking at here have to do with two different things. We have the metal or the semiconductor that makes up a crystalline solid. And just for illustrative purposes, I'm going to put it in a simple cubic structure, just because that's the easiest for me to draw. I would have to actually look up, we had the gallium arsenide, I think it takes a zinc blend structure, which is not one that I expect you to remember. It's a cube that has a base center cubic, or maybe it's a simple cubic, but it's got some other interstitial parts as well. So it's not exactly like this, but we've essentially got this cube. This is going to give rise to our bands. Right? We're going to have some energy level associated with each of these atoms, and each one's going to be slightly perturbed from its neutral, from its standard, individual atomic energy. So we end up with a bunch of things that are kind of close to that, and then we've also got the next highest level, which is also going to create this band. And we're going to have some gap associated with this. Now, we can talk about the things that control this gap. And generally what we said was there's this, if we roughly relate it to the Coulomb force, there's this 1 over r squared dependence. So that means, I'm not going to say it's equal to, but it's proportional to, right? So that means if these atoms get closer together, that's going to make the energy gap larger, because this is going to get smaller, the whole thing's going to get bigger. So there's two ways that we can make that happen, right? One is, if we erase one of these and we put something smaller in there, that's going to make everything kind of fall towards that and scrunch up a bit, right? Or if we kept this all the same, but then we cooled it off, that would make everything scrunch up a bit again. And this is, again, this is the rough kind of hand-wavy answer to it, right? This is not the whole truth. This is just enough of the truth. But it gets us the right idea. So we can say that as temperature decreases, because we could also talk about energy level populations, and we can talk about the electronegativity and the Coulombic force between the electrons in a sea of electrons model. There's a lot we could talk about, right, to get to those deeper answers. But for us, we can pretty much say anything that's going to contract these distances for a semiconductor, right? There's going to be an important difference. For a semiconductor, anything that contracts these distances is going to increase that energy gap. So, smaller distance. These two. And I can't put equals because it's not equal to, right? It just leads to. So, with temperature in a semiconductor, cooling down these atoms so that they all get closer together, you're losing their vibrational energy. That reduction in vibration, well, yeah, that's the other thing. Is why does cooling things off make them contract? That's a whole separate question, right? We can talk about that on the atomic scale. But for now, let's just say cool things down, they get closer together. Has to do with vibrational energies and the motion of the atoms on the atomic scale. But let's just say these atoms are going to have an average distance between them that is smaller. That average smaller distance is just going to tweak this a little bit. It's not going to be a lot, but it's going to tweak that a little bit. It's going to make that gap larger.
And so then the voltage drop would therefore increase because the band gap is increasing.
Yeah. So when we think about the voltage drop, because there's two things we can look at here. Right? We've got voltage drop and we've got wavelength emitted. Right? We were thinking about those two aspects of what's going on. Now the voltage drop, I should actually write these in two different colors for fun. The voltage drop is going to be essentially the energy it takes to excite from whatever these energy levels are up. There's going to be some voltage that's required for that. We're going to be exciting from like a band of energy levels to a band of energy levels because we can't just target one atom, right? And then the wavelength emitted is essentially going to be the same thing but the opposite process. So this tells us, and there's no guarantee that we're going to be dropping from the same wavelengths and emitting and exciting to the same, dropping to the same energy levels and exciting to the same energy levels. But is going to be the same general range. So we should see some correlation between the voltage drop and the wavelength emitted. And that should also relate to the band gap. Right? All of those things should be related to each other. Notice the voltage drop and the wavelength emitted are not exactly going to be the band gap, because the band gap would be from the top of the band to the very bottom of the higher band. But they're going to be approximately related.
So then how does intensity tie into that?
Intensity, this is one of the questions that was asked at the end of the class. Let me check something real quick. Okay, so did my settings? I think my settings got messed up and my video is going to be super chunky. That or the internet's just being slow, so it looks like it's going to be chunky. Okay, so when we think about intensity, that's pretty much a different phenomena going on. Right? Notice when we think about, and the reason intensity is a bit quirky is because people used to think intensity should be related to energy, but it's not. Right? All of this stuff, this is all related to energy, wavelength, voltage drop, band gap, that's all related to energy. Intensity is not actually related to energy. Right? It's related to power. It's related to a rate of energy. The wavelength tells us the energy, the intensity tells us how often that energy is being delivered. So, and then we also have to deal with the fact that it's the way we perceive intensity. And the easiest way for me to make sense of that is to say, if we look at a plot of wavelength versus amplitude, right? You could also say that this is, if you remember, we put our spectrometers into intensity mode, right? So I can actually just erase this and I can just say, that's intensity. Now, if you pointed your fiber optic at the LED when you were at room temperature, you got one shape. Something like that had a peak. We could say, look, that's going to be our lambda. Notice it's someplace in the range of emissions, but we're going to take the middle of the range. And this would be at room temp. As you cooled off, you saw it shift and get a little bit taller. Right? The shift over to a lambda is described through this process. That's the shifting wavelength. The tightening of the distribution is essentially because when we go to these colder temperatures, we're essentially just going to be sampling a smaller range than at room temperature. I should change this. Again, I want the colors to all match. Right, so having this smaller range of transitions is going to mean that the profile of wavelengths is smaller, which is going to give this appearance of increased intensity. Right, so if I integrated all the area under this curve and all the area under this curve, they're going to be approximately the same. There's some other phenomena that makes so they're not exactly the same, but they're going to be approximately the same. But the range of wavelengths gets tighter, which gives this appearance of increased intensity. Right? So essentially, we're getting more and more photons at the same wavelength, which is more intense for that particular wavelength. Notice, if I compared, if I could somehow compare these wavelengths, those would actually have the same intensity still, regardless of the temperature, at that wavelength.
Right.
But at the wavelength of emission, the lambda max, we're going to see this increased intensity because we're narrowing the bands that we're sampling.
Could you talk instead about how, because the voltage drop is increasing while current, I'm assuming, stays constant, then power increases?
Yeah, if you wanted to do it from a EE type standpoint, essentially current is also a measure of energy and time, right? What is current? Volts per second?
Is it current just amps?
Amps. Oh yeah, but what's amps?
Oh, I don't know what amps is.
Right, but current's a time-dependent thing, right? So I'm pretty sure amps is volts per second. I have to check. Watts is joules per second. Oh, I have to check.
So you could say that power is increasing because the voltage drop increases, therefore power is related to intensity.
Yeah, so, you know, since we are delivering the same amount of energy in the same amount of time, but we're seeing more, well, since the time frame's not changing, but the voltage is changing, we can say that's related to a change in power, which is related to a change in intensity. That would be like an electrical engineering explanation for it. I'm more interested in kind of the material chemistry explanation for it.
Okay.
But that explanation is also valid.
For the superconductors part of the lab, the drawings, was it okay that I drew them horizontally? Like
Yeah.
that?
Yeah, hopefully the LAs will be able to make sense of that.
And then on the first one, the pink one, there are like two ways you could like interpret like the simplest cube of the structure, like because we don't know like what it looks like next to the next simplest cube. And I don't know, I interpreted it slightly different from other people, where like basically the I wish I had like an example.
Mm-hmm.
I basically drew it with the empirical formula of Y1 BA1 CU2 and O5. And
Okay.
I don't really know. This probably isn't helping your video.
No, that's okay. That's okay. Don't worry about that. This is just it's not important. So what we have to think about is, regardless of how we interpret the unit cell, everybody should get the same thing. So remember, with our unit cell, we have to cut off the faces. Right? So all of the corners are going to be 1/8, all of the faces are going to be halves, all of the edges are going to be quarters. So regardless of which way you drew it, that simplest repeatable unit should still be the simplest repeatable unit for everybody.
I like the thing that like
Let me take a look.
I drew it like this, so it's like in the pink drawing,
Uh-huh.
it was a little bit wider. Like there was another oxygen and oxygen.
Did you not include the other parts?
Like I would try to make it simpler.
No, you have to include everything. Do you
So-
still have the picture of it?
I have this one on my phone, and that one I never really got.
Okay, well, you were supposed to get both on your phone. So look at this one, the pink one on your phone. You can't eliminate atoms. You can't just not draw them. They're still there.
Okay, I was just like eliminating them because I thought like you wanted us to like make it simpler, so we
No,
that
you were
was the
giving,
simplest.
that was the simplest. You can't eliminate atoms from the unit cell.
Okay. I didn't realize that was the unit cell.
That was the unit
Can you
cell.
take a look at mine? I'm not sure,
Sure.
if I'm doing it right.
I think you're on the right track.
Okay.
You got your different shadings. You've got the different ways you're drawing it.
Right.
You've got your similar layers. It looks like you're on the right track. I would
Okay.
have to actually look at the structure to
Okay.
tell.
So, but because it's like a superconductor, it could be like divided into like technically 3 squares, 3 unit cells, or
Not
not-
actually.
okay.
Because of because the unit cell, remember, the unit cell is the simplest repeatable unit.
Mhm.
And because it's got that ytterbium sitting in the middle of the whole thing,
Right. Uh-huh.
that ruins it, so you can't say, oh, this little bit, even though that bit on bottom is like the bit on top,
Uh-huh.
you still need the ytterbium in the middle of that structure to get it
Okay.
repeatable.
Gotcha.
Y'all still didn't ask the tricky questions.
Superconductor power?
No, it wasn't the
It's a,
superconductor.
how does superconductor like cause like the how does decreasing the temperature of a superconductor increase its dipolarity or diamagnetism? Is that the trickiest question?
No, that's just a lookup question. That one, the Meissner effect is just like you look it up and you just end up with this situation where a superconductor is essentially a conductor where you get temperature contracts these bands enough that you become a conductor in a material where you don't expect to become a conductor, and you end up with zero resistance.
Oh, that's why the magnet floats.
Yeah.
Is
So-
it because because the temperature is but doesn't colder temperature increase the distance? Oh, but not for superconductor.
Not for superconductors. Superconductors do something funny, and that's kind of the interesting thing. Superconductors, when you start contracting things, you actually get better orbital overlaps between things. So essentially, those ytterbiums get closer together, but when they get closer together, their orbital overlap actually changes the structure of
The
this
band gap
thing.
decreases.
Yeah.
But does that not have anything to do with it?
Well, no, it does. I just want to be careful because that's not generally true, right? It's true for different materials. Superconductors essentially are very strange. And I will admit I'm not completely comfortable with explaining how superconductors work. But essentially the part that I do know is you hit a certain temperature and they exhibit zero resistance, right? Suddenly the electrons can move without anything blocking them. And that's really unique.
Okay, so that's basically all we had to put together.
Yeah.
Was like that no resistance means. But how does that relate to the magnet? If there's not.
So this gets into physics, and this is really like, oh yeah, this was a question that I was expecting most people to just look up. So essentially, what happens is, if you put a magnet next to something that can conduct, the electrons in that material start to move around a little bit from that magnetic field hitting them. But if you put a magnet next to something that superconducts, those electrons just fly around so fast that they actually create their own repulsive magnetic field. You get magnetic induction. And so that magnet essentially creates, like, a superconductor essentially reflects the magnetic field back at the,
From its own electrons?
and electrons. We've got two materials here. We have to be very careful with our
What are the two
language.
materials? What was in the cup? In the
Liquid nitrogen to get our superconductor to the coldest temperature possible to get superconductivity.
But wasn't there a metal inside that? cup too.
That the little disc.
That was a superconductor. Right?
That little disc is the superconductor. It was a blackish gray superconducting material.
And then the black square.
Magnet.
The shiny silver square. The shiny silver square was the magnet,
Okay.
and that was a neodymium magnet, so a really strong magnet
So where's the electrons?
everywhere.
But whose electrons?
You tell me.
Everything's. I think it's from the metal circle or whatever.
The metal circle.
Not the metal magnet.
So again, precision with language is really important in this case because we have multiple parts. We have the cup that has liquid nitrogen in it. We place the superconductor in the liquid nitrogen. That superconductor is the disc. It's not a metal. It's a composite material, right? It's ytterbium, barium oxide, the copper oxide, the thing that you just drew. It's that. That big pink structure, that is what makes that disc. When that disc gets cold enough, it exhibits superconductive properties. Now the question becomes, what's the easiest way to show you superconductive properties? We could attach some electrodes, we could measure like the resistance across the material, and what we should see is it's got resistance, as soon as it hits 77 Kelvin, or a little bit before, I think it's like 85 Kelvin, the resistance suddenly drops to 0. Right? That's one way we could have demonstrated it. The more fun way, the more interesting way, is to take a neodymium magnet and put that neodymium magnet close to the superconductor once it's in its superconducting state. That neodymium magnet's magnetic field will induce a magnetic field in the superconductor, and then it'll repel itself, or the two materials will repel, and you'll get that flotation. Again, I was expecting people to look this up.
Okay, shoot. I was like, I can think about it and figure it out.
No, I don't think you could just think about this and figure it out. I was expecting that you all have and know how to use the internet.
That's good.
You have the internet? You know how to use the internet?
I don't know when to use the internet.
Always use the internet.
I'll keep that in mind.
Always use the internet. So the thing is, we're at a point in our, like, I know in high school they're like, don't use the internet, don't use Wikipedia, blah, blah, blah. But the fact of the matter is we're at an educational point where if you can Google it, it's probably not the most interesting thing, right? We are looking more at combinations of ideas. The Meissner effect, the superconductive effect, that's just a simple kind of like, hey, how did this happen? And it's really in the realm of physics more than it is in chemistry. But like I said in class, the reason I really enjoy these materials is because it is a combination of like a lot of different subjects. No one's asked the tricky question yet.
Maybe it just wasn't tricky for us.
Maybe it wasn't tricky for you. Maybe you all got it. Which is great.
Or you can pause the video and give us a hint on what to ask.
Yeah.
Oh, it's the phosphorus one. Is that what you want?
Nope.
No.
Amps is coulombs. Sorry, I've been wanting to picture amps is coulombs per second.
Oh,
Coulombs
per
is
se- yeah,
coulombs per second, right? It was just charge, which is,
Yeah.
we can relate. What did you? So I'll just ask and see what you all said. What did you say about the conductor's properties in hot and cold temperatures?
It said as temperature decreases, conductivity increases, because the colder temp will yield lower resistance because atoms won't be vibrating as much, allowing the electrons to flow more freely with fewer obstacles.
Yeah. Great. Okay. Never mind. It wasn't tricky. You're all good. It was tricky for my last class. I didn't get it. It's also one of those things that in my mind is tricky because again, it is a hand-wavy physical explanation, right? The same way that I said, oh, these all get closer together. There's more going on there, right? The idea that, I mean, our understanding of resistance and conductivity from a physical standpoint, I should say a physics standpoint, is just kind of like an electron moves across the whole thing, right? That's not really what's happening, right? When you get actually into electronics, do we have any EE majors? No. Okay. When we actually get into like the details of circuitry, you have your conductivity, which is how fast the electrons can appear to move across, but then you also have a drift speed, which is how fast the electrons actually move across the material. Because what's actually happening with conductivity is this thing. Let's see if I can make this work. So when one electron comes in, it just knocks the other one out the other side. It's not one electron traveling across the entire material.
That's how the holes work, right?
Yes. If we wanted to get into the holes and extra electrons, which is the N-type, P-type doping,
Right.
that changes something called the Fermi level, which is not something that we're getting into in this class. It kind of has to do with how big these spreads are that we're exciting to and relaxing to, kind of. And so by adding different materials, we can change which bands we're going from and to, and how much energy it takes to get over. Without thinking about it, we just say it's just directly in the middle of the band. And that's going to be the amount, that's going to be the energy it takes to get over it. But if we kind of like stack the bottom or stack the top, we can make it easier to jump across or harder to jump across. It's another way we can tune the diode. Homework questions?
I have some questions on the midterm.
Okay, I might go ahead and stop the video.
Go for it.
I wanted to make sure we had a video about the lab. I'm going to send this out to everybody in case they did not get all those things in class.